that's the wrong title. So I'm Theodor. I work in Sweden, as we said, and last year I completed a 3-month internship in Berlin at the company Data Artisans, which are commercially supporting the Apache Flink platform. So I'll get right to what we're going to talk about a little bit today. So large-scale machine learning, I want to make it like a distinction between what is considered by many people large-scale versus small-scale. So what do we mean when we say large-scale machine learning, right? So in order to have large-scale, we will need to have something as small-scale as well. So this is a definition from a very good researcher that we do, which is currently at Facebook AI Research. So small-scale learning is when you have data points that can actually, let's say, that are actually your actual budgeting stage. So if actually getting more data points for your problem is too costly, then you would have a small-scale learning problem. For example, if you're trying to run some kind of survey and you need to include people in it, and you need to pay each one of them, it's a small-scale learning problem because you're not limited by nothing else except for the actual number of data points that you have. Now, when we talk about the large-scale learning problem instead, the active budget constraint that you would have is the time. So data is plentiful, so you are a big company, you have millions and billions and trillions sometimes data points, but you need to some way to process all those things in a reasonable amount of time. So for example, if we're trying to do daily recommendations at Pandora, and that computation takes 1.5 days, it's not going to work, right? We need to make it work somehow within the time constraint that we have, which is daily. So this is the type of learning that we are actually concerned with FlinkML. So first, for the people that are not familiar with the Apache Flink platform, I'm going to give a very brief introduction. If you want more, you can definitely ask me about it later. So Apache Flink is a distributed data processing system, and at its core lies a streaming data flow engine. So it provides powerful, easy-to-use APIs for batch and stream processing with a lot of, let's say, functional programming style paradigms. And it's a technically advanced engine with many features that make it a very good candidate to write machine learning applications in. So we're going to go through them right now. So some of the things that are also very advanced in the engine we're going to mention later, but it's not going to be the focus for now. So this is the Flink stack, the current Flink stack. It works well within the Hadoop ecosystem. It allows processing from multiple data sources. It has high availability through Zookeeper. And on top of the data processing APIs, it also provides libraries for SQL-like queries on batch data and streaming data also, graph processing through the Jelly library, and machine learning, which is what the talk is about. So what makes Flink a good platform to write ML programs in is these three features, and we're going to look into how they help us as a developer for machine learning. So the first one is expressive APIs. So for both in batch and stream processing, we have this functional style syntax and SQL-like commands like group by. And these allow for the quick development of machine learning algorithms, and it gives users, let's say, a familiar way in order to program. So you don't need to relearn paradigms in order to program in Flink and be able to run your distributed applications. Another very important part of Flink is the core processing engine, which is a streaming data flow engine. So what that means is that using this engine, you establish your operators at the beginning of your job when you deploy your program, and then the data continuously pipes through all each operator without any explicit processing stages. So this makes real-time stream processing possible. And one thing that this streaming engine allows us to do is actually to have iterative data flows, and it provides native iterations for machine learning applications without materializing the intermediate results. So in a batch engine, let's say like Apache Spark, when you have an iterative application, let's say, and most of the machine learning applications are actually iterative, at this stage you actually have to stop, materialize the results, save them to run in order to be able to process them fast later, and then resubmit at the end of each iteration. So it's basically like a for loop that you unroll, and you create this dependency graph that can become really large, and in some applications that can be problematic if you go very deep within iterations, let's say. So in Flink, what we're able to do instead is that we're able to maintain a partial solution. So think of a model, let's say, in a machine learning application. So we keep that model as the current state of the iteration, and we just iterate by updating the model within the data flow itself. And we are able to actually, we don't have to schedule to perform any additional scheduling. We just are able to have a model iteratively there, and we're able to query it as well. So in addition to this normal batch iteration, Flink also provides delta iterations. Now, what delta iterations do is they allow us to shrink the size of the program as we get closer to its solution. So in this example, I think it's PageRank. When you start with a graph of 1 billion data nodes, at some point most of the graph will actually converge. So you don't need to iterate through the whole graph as you approach the solution of it. So what we're able to do with Flink is that as we get closer to the solution of the problem, we're actually able to shrink the size of the problem, making it much faster to compute. And this can also be applied to a lot of machine learning problems. So another thing that is very important that I mentioned before is the performance of Apache Flink. What it provides is high throughput and low latency stream processing. It has its own memory management, so that means that you get rid of most of the out-of-memory problems that you might encounter usually. It provides things like exactly one semantics and event time support for streaming, and also for fine-grained fault tolerance. And these are some of the figures that Jamie Greer, who was formerly at Twitter and now works at Data Artisans, he explains this in a blog post about how they were able during the Twitter Hack Week to build a prototype, taking their original system in Apache Storm, build a prototype in Apache Flink that was able to do the same thing that they were doing. You can think about adding impressions, let's say, going through your streaming and then performing your computation on top of that. And they were able to actually transfer that whole job into Flink within the week, and actually create a system that uses less than 1% of the resources than the previous system and has higher accuracy. So, moving on to FlinkML. Yeah?
On the previous slide, the right, what's the y-axis there?
This is the milliseconds. Yep. Right, so moving on to FlinkML. So the development of FlinkML started the previous spring, and the first version is already out, let's say, included as a beta library, let's say, in the Apache Flink distribution. And I should mention that it's written in Scala, but we do plan to have support for Java as well. Flink itself is written in Java, and it has APIs for Scala, and a primitive API also for Python. So moving on for the goals of the library, we have 3 goals in mind when we started the library, right? So the first one was to have a library that is truly scalable. So we want to have efficient algorithms, and we want the implementation that can deal with web-scale datasets, like datasets that major companies might have to deal with. Another thing that we want to avoid is glue code. So currently, when you have a machine learning pipeline, let's say in a normal production system, you would have to patch together a number of the different services. You would have something to ingest your data, something to pre-process your data, your actual machine learning logic, something to check the model, and then some other way to serve the model to the users. And that creates a lot of glue code. And according to a recent Google publication, mature ML programs are actually 95% glue code, and only 5% is actual logic. So what we want to be able to do with FlinkML is actually minimize that need for glue code. And then the final thing that we want to make sure is that it's easy to actually use the library. So we want to have high quality documentation, a lot of examples, and follow the example that is said, let's say, by scikit-learn, but do it in a distributed processing library as well. So we take a brief look at the algorithms that are currently available in FlinkML. So starting with supervised learning, we have a generalized optimization framework that includes stochastic gradient descent. It includes supervised learning methods like support vector machines, and we also have multiple linear regression. We provide a highly scalable ALS implementation. And for pre-processing, currently we have polynomial feature scaling, and a couple of others, and these are, I think, some things that will be extending in the future in order to be able to create, let's say, machine learning pipeline. And we also have a new algorithm for exact KNN search. And one feature that we took care to include from the beginning was machine learning pipelines. So these allow for the development of complex, let's say, sequences of machine learning tasks with minimal code. So let's take a look at how easy it is to write a program with the FlinkML. So using standard Flink commands, we can just read the train and the test set from STFS, for example. And then we can set up our learning. Let's say in this case, it would be a multiple linear regression case. And then we just code fit as we would, let's say, in sklearn locally. But this would actually run this cluster, of course. And the fitted model can now immediately be used in order to make predictions. So in less than 10 lines of code, you have a fully working simple learning system that can scale to your needs. So I would also like to demonstrate how easy it is to create a machine learning pipeline. So here we will train a regression model after passing our data through a standard scaler and augmenting the features through a third-degree polynomial. So this is our setup here. And we construct the pipeline by chaining together as many operations as we need. And then we use the same commands, fit and predict, on the pipeline itself. Right? So again, we are able to have easily powerful pipelines with minimum input here. So to continue, I would like to take a look at some of the cutting-edge algorithms that we use in FlinkML in order to make sure that it's a truly scalable platform. So for alternating least squares is a commonly used collaborative filtering algorithm for recommendations. It was developed in the context of the Netflix prize. And it's basically a matrix factorization algorithm that allows us to approximate this user item matrix with two smaller matrices that can represent latent factors. And so what needs to happen for alternating least squares is that we need to have access to both the data and the model during our computation. And in a distributed setting, of course, this will lie in different machines, right? So if you naively implement the algorithm, you would have to maintain copies of both the data and the matrix approximation at this worker. And for each rating block that we would have in Y here, we would have to send a copy of that column to the worker. So that would quickly cause problems because we are sending perhaps multiple copies of the same data to the same worker, and we are creating unnecessary network load. So in FlinkML, our strategy is instead to break up the rating matrices into blocks and only send the model blocks as needed, avoiding any kind of extra unnecessary load. So we are actually batching together all the, let's say, all the model traffic that we need to do in order to minimize the network. So this allows us to scale the learning to matrices with 28 billion non-zero entries in a 40-node cluster, which is similar scale to what companies like Netflix or Spotify or Pandora might have to deal with. So first, I would like to talk about a relatively new communication efficient optimization algorithm. So stochastic gradient descent is perhaps the most widely used optimization algorithm and is very popular in areas like deep learning. Its strength comes from the simplicity, and the most distributed implementation actually uses a simple synchronization scheme, but that one has a high communication cost and creates slow updates for the model. So you can do better than that. So COCO, or Communication Efficient Metascent, is an algorithm developed at Berkeley by Yagi and Mike Jordan and a few others. And this one aims to reduce the communication cost in an optimization problem and achieve faster convergence. And it uses a number of tricks to achieve that, which we will explain now. So the first one that they do is that they switch the optimization problem from the primal problem to the dual problem. So this is a simple transformation. So what we're able to do is basically create the dual problem and transform your minimization problem into a maximization problem. So, okay, you can ignore maybe the math here, but what the dual problem gives us, basically it gives us an upper limit for what the minimization problem is. So by achieving a solution for the dual problem, we're actually able to approximate the solution for the primal as well. So for this kind of problems, coordinate descent methods are commonly used, and they give stronger results than primal only methods like stochastic gradient descent at the same iteration cost. So they require no step size, which is a major problem usually with stochastic gradient descent, and they have a well-defined stopping criterion, which is the duality gap. So another problem with the distributed stochastic gradient descent is that we update the model at the end of each iteration, at the end of each run, and then we do that by syncing all the workers. So as a result, some workers may optimize the stale model for long periods, or we usually have increased network load as well. So in Coco, the updates are done locally at each worker, and we make sure that the local model is at least updated without syncing with anyone else, and thereby you reduce the communication cost. So as an illustration of how the model works, every worker solves a small local optimization problem using dual optimization, any dual optimization method that you might want, and it keeps its local model updated. So at the end of the local iteration, you sync the workers to update the global model and begin the next super step. So the reduced communication and smarter optimization can have great effects for the convergence and speed of the algorithm. So Coco is the red line here, and the y-axis is on a log scale, so it beats local and batch versions of stochastic gradient descent and coordinate descent, sometimes by orders of magnitude. And the SPM implementation that we use in Flink is actually using Coco for optimization. So it has good performance, Coco, but it has one important disadvantage. So communication still happens with the barrier. As we said, at the end we have a super step and we have to wait for everybody to finish. But what happens if we have stragglers in the cluster? So stragglers in the cluster are machines that are working much slower than some of the other machines because of any number of reasons, and this is very common in large clusters right now. And we're going to talk about some recent research from CMU with Professor Eric Zink, and that deals efficiently with stragglers. So the different synchronization schemes that we have available in distributed setting. So first one, we'll take a look at bulk synchronous parallel. So here is the case that we described before, where synchronization acts as a barrier. The fastest workers always need to wait for the slowest one in order to catch up before moving on to the next iteration. And in the presence of stragglers, this can cause many performance issues. The other approach is to have an asynchronous parallel, so we remove all barriers and we let all the workers work as fast as possible, and algorithms like Hopewire, for example, are an example of that. But although this technique can be fast, it can often be the case that because of the different versions of the model that different workers are optimizing, we can actually end up diverging with the solution. So what Zink et al. Actually proposes is to have this stale synchronous parallel model. So the fastest workers in this model can only be up to k iterations ahead of the slowest workers. And if they are about to move further ahead, then they stop and wait for the slowest one to catch up. And this allows for progress, while also keeping the fastest workers working and allowing for faster conversion. So if we look at it in a figure to make more sense of it, if we have the fastest worker 1 here, and we have, let's say, a threshold of 3, if the fastest worker has already completed iteration 6 here, and worker 2, which is the slowest one, has not really reached iteration 4, it will have to wait until worker 2 also has reached the clock 4 there. So looking at the performance of this state synchronous parallel implemented in Flink, and we use here a parameter server in order to sync. So this is a lasso regression, distributed lasso regression done in Flink, and we have a cluster where we have generated load. At any time, one random node gets 100% CPU load for 12 seconds. So here, we can see the convergence level. So this is the bulk synchronous parallel, and the SSP on one side, the steady synchronous. And we can see that we can actually obtain better convergence than the bulk synchronous parallel. But most importantly, we can see that the time for convergence is much less than once for bulk synchronous parallel, even in the presence of stragglers in this case. So this is a submitted PR, and once we get this merging, it will be, to my knowledge, the only implementation of state synchronous parallel iterations in a general purpose process. So I'm going to talk about a little about challenges in developing an open source machine learning library. So this should be quick, I hope. So generally challenges when developing a machine learning library. So first one is the decision between depth and breadth. So given the limited resources that you have as a developer, as a group of developer, we can either choose to, let's say, satisfy most people and include like a different enlarge the number of different algorithms, or we can try to just optimize a few algorithms and make sure that we get them right and they are scalable. And this choice that we're perhaps leaning towards having a few good algorithms instead of a wide range of algorithms in Apache Flink. In terms of design choices, there are many choices that one can make when developing a machine learning library with not so obvious consequences. For example, when you train a model and you call fit on your trained dataset, you have a model that is trained, right? So you can either return an object with that model, or you can keep the original object that you called fit on, like scikit-learn does, for example, and then you have your trained model attached to, let's say, your algorithm. So Apache Spark has decided to do it the other way, where when they call fit, they actually return an object and then you can use that. So both of these choices have the advantages and disadvantages for them. So for example, for Spark, it's perhaps easier to actually serialize a model later and deploy it to production, but it also creates a usability concern for users that have to care about where my algorithm lives and where my model lives, and it can become confusing, especially for new users. And in terms of testing, in any case, for probabilistic results are notoriously difficult to test, and it's in the nature of machine learning algorithms that some parts will actually be unsure about what should happen. And using scikit-learn as the ground truth is not the solution, as many libraries currently do. And that was one problem that the core developer of scikit-learn actually mentioned, that they're not able to actually test for the correctness of their library because everybody else tests against them for the ground truth. But this is definitely a problem, and we have to use probabilistic techniques and create tests that actually give a lot of load to the testing servers that we can. And concerning challenges about developing the open source, so attracting developers is a major problem. So machine learning is hot. Everyone has a machine learning library now. Like on the train, I did a search on GitHub for ML. I got 25,000 results, so there's like, I don't know how many of these are libraries. But at this point, there are probably more libraries in machine learning than there are developers that can support them. So, for us being under the wing of a popular Apache project like Flink, it's definitely helpful, but it's definitely challenging to attract more people. So, even if you are lucky, let's say, to get enough developers, then you would have the problem of deciding what to commit. And it's not always clear what to keep and reject for the library. So with machine learning being so hot in the recent world, we get new algorithms basically every day. And researchers want to see their code implemented somewhere that is popular, that is called impact. Let's say if you are from a funding agency or something, so that's really good if you can get it in something that has 1,000 GitHub stars, for example. But we cannot ignore any new learning rate algorithm that for stochastic descent that comes up. So popular libraries like, for example, scikit-learn, they have, let's say, the luxury to be very selective about that. So they have actually a limit of that the publication needs to have happened as a rule of thumb at least 3 years before, and the paper must have gotten at least 200 citations in order to be merged into scikit-learn. And in our case, I'm not sure if we have that luxuries, but we need to be selective but reasonable. So you definitely want to avoid discouraging developers by rejecting some work that they have put in a lot of work in. But at the same time, you want to avoid committing too much code into your library because it will lead to the next problem, which is code rot. So code rot is about developers mostly. So since finding developers is hard, maintaining code is actually harder. So for every piece of code that you take into the library, somebody will have to maintain it afterwards. And since in an open source library like Apache Flink, most of these people are actually doing this on their free time, you want to make sure that every piece of code that ends up in the library is actually worth being there and it's worth maintaining for the next few years. So for the current and future work on FlinkML, currently we're working on creating an evaluation and cross-validation framework. We work on distributed linear algebra to make it easier to prototype, let's say, some new machine learning algorithms by using simple linear algebra techniques. And we're working on getting streaming predictors out. So if you have your ALS trained, you want to make sure that you're able to deploy it and make streaming recommendations out. For the algorithms, we're working currently on an implicit version of the ALS algorithm. We have an open PR for the multi-layer personal neural networks algorithm. And we're looking at streaming decision trees and columnized statistics. So all of these are open PRs that we hope we'll be able to merge soon. So in terms of the long-term plans for FlinkML, we want to focus on streaming. So the strength of the Apache Flink as a platform is actually the streaming capabilities of it. And what we also want to be able to do is take advantage of this, let's say, very advanced processing engine that we have, and make sure that we're able to implement the latest online learning algorithms, and also do it in a manner that is similar to our philosophy of development. So we do plan to kickstart the machine learning library at my research center as well, and we also will be looking for real developers in the US and other places. So check it out if you want. We have a website and the docs, and if we have too much time, I don't know, I can 5 minutes. If we have 5 minutes, I think we can go straight to questions. I had a demo because I couldn't get everything to work, so I could go through something like showing you pictures of Apache Zeppelin and how you can do this, but I don't think that's very exciting. But it's possible. But yeah, as I said, I think we can go straight to questions here.
Hey, Theo, one quick can you repeat the questions that you
Yes.
so it gets recorded?
Sorry. Yeah.
How does this compare to Apache Spark and possibly also TensorFlow?
Alright, so let's start with TensorFlow, which is the easiest to compare, so to speak. So TensorFlow is not a distributed processing engine. TensorFlow is, I would say, built more for computations that are done locally or within a number of GPUs, and it's specifically aimed at linear algebra processing. The base, let's say, unit of understanding in TensorFlow is tensors, which are multi-dimensional matrices. So you're able to do a lot of very great machine learning tasks in TensorFlow, but the let's say, extra advantage of Apache Flink is that you're able to do all the pre-processing that is needed and all the post-processing that you will need to actually deploy the model within one framework. But TensorFlow is basically a learning framework, only for machine learning. So in terms of Spark, yes, there are a lot of similarities with the project. I would say that there's definitely a competition between the two frameworks. So I would say that there is room for both of them. So Spark is, it has a very good engine for batch computation, but the fact is that because of the way that their engine is built, which is a batch engine, which means that whenever they want to do regulate, let's say, streaming in Spark, they actually have to batch a number of examples. So if you have data points coming in, you would have to batch, let's say, 10 seconds or 5 seconds or a number of examples, create an RTD, which is the resilient distributed data set, and then actually process it, and then because the RTD is an immutable structure, you will process it, create another output, and process it in turn. So as I said in the beginning, the main difference with Flink is that you would actually get your operators, and you would have the data streaming through the operators themselves. So each data point would actually go through all the operators during the processing without actually having to wait for, let's say, batches to arrive. And that is what enables you to do real-time streaming instead of emulating. Yeah?
So question here, is the Flink architecture compatible with vector processing via GPUs? And if that is the case, then how much of this work that you're doing to optimize numerical computations would need to be redone for vectorized computing on GPUs?
Yeah, so the question was whether Flink can work with GPUs as well. And the answer is that we can at the higher level. So since we are using, let's say, optimized libraries in order to do most of our linear algebra computations, for example, we will be using Breeze, that in turn uses other libraries like Netlib, that in turn use basic linear algebra subroutines libraries, blast routines. So we're able to do it at that level. We're not accessing the GPU directly, but if, for example, your BLAST backend is actually NVBLAST, which is the implementation from NVIDIA, then you will be using your GPUs in order to do the computation. But this is a major problem, and it's something that I'm personally working on in research, because not using GPUs if you're going to do machine learning is, I think, a big mistake, and it's definitely something that we'll be looking at in order to make the computation as efficient as possible.
Thank you.
Thank you. Any more questions?
Any similarities with Storm?
Yeah, so Storm is, I would say, a previous generation stream processing platform. So in the benchmarks that I showed you, the first, let's say, the item there that was doing the slowest was actually Apache Storm there. So it is also a stream processing library, but it lacks a lot of the functionality, capabilities, exactly ones, guarantees, fault tolerance, and all of the things that Apache Flink provides. So I would say that Apache Flink is an evolution, that the lessons that you learn from Apache Store are being implemented on completely different ends.
Did you say that was because of the connect between the two clusters?
Sorry?
Did you say the slowness is because of the lag between Spark and Kafka?
Yeah, so one of the bottlenecks that they found at Twitter was that Kafka was basically not fast enough to feed Apache Flink with data in order to process it. Because Flink has such a high throughput that Kafka could not. Kafka with the combination, they had I think a key value store somewhere in there, and they were trying in the Yahoo benchmark, they were trying to query the key value store, and that created kind of the bottleneck along with Kafka. So what the guys at Twitter did is that they took the key value store out, put all the processing inside Flink, and actually query the state inside Flink. So that allowed them to go from like 4 million events per second to 15.
So how do you position Flink? Do you view yourself as a direct competitor of Spark?
Well, I am a contributor to the Apache Flink project, so I'm not competing with anybody. I'm just but if you ask me, I would say that there's definitely room for both products to exist. So Apache Spark, as I said, it's a very popular product and it's very mature already, and it has a focus and a market segment for the batch processing. But we see that a lot of processing is now moving on to streaming, and I would say that that's where the area where Flink would shine the most, and that's where the focus for the development of Flink is. And as I said, with machine learning, we plan to do the same and move, let's say, our development efforts into online learning.
So Spark has streaming now too.
Yes.
So in that area, do you do some benchmark compare the two?
Yeah, so there are a few benchmarks comparisons. So in the slides, you will find a few references that I have, and there was one that came out, I think, a couple of days ago from the API Institute in France, where they only compared for the batch aspect of the two processing engines. And there you can see some things that they mentioned, like that Spark is faster in some cases, Flink is faster in some cases. They mentioned things like the necessity of Spark to control a lot of different parameters, whereas that is not necessary with Flink because it has its own memory management and that kind of thing. But I would say there's definitely room for both products to exist, and it's up to the specific application which one you end up choosing. Yeah.
See, I definitely see the advantage in terms of streaming, because like Spark is not like real-time streaming. There's some kind of delay there.
Yeah.
But if my understanding is correct, actually Flink started on 1 year before Spark. Like why Spark generated so much, created so much attention was Flink, and like people rarely know about Flink.
Well, why people rarely know about Flink? I mean, Spark was definitely the first distributed data processing engine to come out, and I think that it could be any number of reasons. It could be the fact that AmpLab is very popular and they're able to, of course, popularize the platform itself, could be a reason. Or it could be that at the point, Spark was much more advanced as an engine than Flink at that point, right? Because Flink started actually from a European research project, and by the time that they actually got to release it, Spark had already gotten a huge amount of popularity. So I think that it's a number of reasons. I cannot tell you why Spark is more popular than Flink right now. It could be first to market, it could be a number of different aspects.
But Spark is more than just machine learning, right? That's the other...
Yeah. I mean, that's the whole point of Apache Flink now. So what I presented today was a library for Apache Flink, right? So when I showed you in the beginning, I don't know if I can go back quickly, no. So in the beginning, Flink is also a data processing platform, so it has a whole stack. So you start at the storage level, which we don't touch, then you have the data processing, then you have APIs on top, and then you have libraries, and now we're getting to the point where we're getting libraries on top of libraries by different people. Is that it? All right, thank you.